Good morning. Now, this is class 4 of our chapter module 3 experimental methods and error analysis. Now, in this class, we will learn how to measure angle or measurement of angle. Okay, that is how to measure small angles, how to measure large angles, and various instruments that are used for measuring angle. Okay, now angle is also used to designate the measure of an angle of rotation. So this particular term angle, it is mainly used in order to denote or in order to designate the measurement of angle of rotation. And another definition is that this measure is a ratio of the length of a circular arc to its radius. Okay, that is actually called as angle, you know that. Now, the unit of angle is radian. SI unit is radian or steradian. Now, today we will familiarize some of the instruments that are used to measure the angle of slope, elevation, or inclination of an object. So, let us begin with an instrument called clinometer. Clinometer or inclinometer is nothing but an instrument for measuring angles of slopes uh, or elevation of an object. It is also known by several names, namely tilt meter, tilt indicator, slope alert, slope gauge, gradient meter, then level gauge, then declinometer, etc. All these are various names used for the instrument clinometer. And the early form of clinometer actually consisted of a flat base on which this instrument was placed, and a hollow disc having a glass top is placed on that base. Then the glass face of the disc was surrounded by a circular graduated scale, that is a circular scale with markings. Then the disc is half filled with a heavy liquid. The scale around the disc indicates the angle at which surface of liquid stands with reference to the flat base. This is the early construction of clinometer and how it was used to measure the small angles or angle of slope, elevation of an object, etc. Now, inclinometer is commonly used in forestry to measure slope, vertical angles, elevation change, height of trees, etc. Now, it is said that a very simple clinometer or clinometer in its simplest form can be made from a very large protractor. Protractor, you might have seen that a narrow piece of wood is glued to the base of the protractor to act as a sighting line. A heavy mass is then fastened to the midpoint of the baseline of the protractor. That was another way of constructing a clinometer using a protractor. Now let us see how a clinometer is used to measure height of buildings, trees, etc. Now from this figure, the clinometer will measure the angle ACD. Here ACD, the angle ACD is marked as theta. You can see that in the figure. Now let angle BEC will be, if angle ACD is theta, then what will be angle BEC? Definitely it will be 90 minus theta. Let us denote that 90 minus theta as alpha. Okay, then what will be tan alpha from that triangle? Tan alpha means, tan theta actually means what? Opposite side by adjacent side. So from this figure, tan alpha will be BC divided by BE. So BC will be BE tan alpha. Okay, now BE actually, as per the figure, it is the distance of the person from the tower. It can be measured. We can measure that distance. Now hence BC can be calculated. So total height of the tower will be AB plus BC. This is just a simple illustration to show you how a clinometer is used to measure inclination. Okay. Another method is scale and telescope. This method you will be using it in the lab. So when you read this theory, you won't be able to understand that much. But when you do practicals in your lab using this method, scale and telescope, definitely you will get an idea about that. There are experiments that you have to do using the scale and telescope method. So then now you just go through the theory. When you do an experiment based on the scale and telescope in the lab, everything will be very clear to you. So now we have no other way, you just go through the theory. Okay, so scale and telescope is an important method. Small angles can be measured using a scale and telescope. As I said, this method is used in laboratory to measure angles and hence to calculate what the thickness of thin objects. Okay, now to determine the thickness of a thin glass plate G, now here our aim is to determine the thickness of a thin glass plate, which is denoted by the letter G. So we are given a thin glass plate and you are asked to measure its thickness using the scale and telescope method. So first of all, what you do is that you place that given thin glass plate below the rear leg of an optic lever. There is an instrument called an optic lever with 3 legs. It will be having the shape of like that with the 3 legs, and you will keep this glass plate below one of the legs of the optic lever. Then so in order to place that glass plate below the rear leg of the optic lever, definitely you will have to raise the whole instrument through a small height, which will be equal to the thickness of glass plate. Okay, so as a result, the metal plate P and the mirror M will get slightly tilted through a small angle theta. Now we have to measure that small angle theta, that is how much that plate or mirror has tilted when you have placed that glass plate or when you have placed that thin glass plate. So in order to measure that particular angle of tilt, you use this particular method, scale and telescope. So on looking through the telescope, there will be a different a reading different from the previous one will be found. To be coinciding with the horizontal crosswire of the telescope. This new reading is taken and the difference in the two telescope reading is taken as small letter S. That is also called by the name shift. Okay. So it is nothing. You are given a thin glass plate and you are asked to measure its thickness. So first of all, you are given a scale and telescope arrangement. So before placing the glass plate, you just note down the telescope reading by looking at the horizontal crosswire reading. You just note that reading and keep it with you. Now you place the thin glass plate that is given to you below the rear leg of the optic lever. Once it is placed, there will be a slight tilt in the whole apparatus. Okay, that is, there will be a slight change in the angle of inclination. So definitely there will be a change in the reading, right? Now you take that reading, that is, just note the reading where the horizontal crosswire coincides. So you have got two readings with you. That is, the first reading is without placing glass plate and the other one with the glass plate placed. Now this difference between these two readings will give you the shift denoted by the letter small letter S. Okay. Next, the distance D of the telescope from the mirror is measured, and after that you take the impression of the tips of the 3 legs of the optic lever on a sheet of paper. The perpendicular distance of the rear leg from the line joining the two front legs is measured as L. That is nothing. I already told you that optic lever is a device with 3 legs. You just take an impression of that device on a white paper. So you will get 3 dots like this. One dot here, one dot here. Join these 3 points. Measure this particular distance, this distance, with using a scale. Okay, that will be your L. Okay, hope it is clear. From these readings, the thickness of glass plate can be calculated as follows. How? Let x be the thickness of thin glass plate. Let theta be the angle through which the mirror is tilted when the glass plate is inserted below its rear leg, that which I already told. Then the angle through which the metal plate P and the mirror is rotated will be given by theta equal to x by L. When the mirror is rotated through an angle theta, the same reflected ray, the angle between the two incident rays must be 2 theta. Therefore, 2 theta is given by the shift S divided by the distance between the scale from the mirror, which is capital D. Okay. So theta will be x by L, which is again equal to S by 2D. Therefore, x will be Ls by 2D. Thus, thickness of glass plate can be calculated. So now you just go through the theory part. Once you do the experiment, everything will be clear to you. Now, another such instrument that you use in the lab is the spectrometer, which is a very important experiment. So now also, just like that of scale and telescope method, you just go through the theory part. When you do an experiment by your own in the lab, everything will be clear. Okay. So spectrometer, it's nothing but an instrument used to measure angle of prism. Okay, let's go through the theory. This spectrometer is a compact apparatus for obtaining a pure spectrum. It is used for measuring angle of prism, then the study of spectra and finding various optical parameters. Its main parts are collimator, telescope and prism table. See, I will just show you which are they. See, this is a prism table where you mount the prism or where you place the prism. This is telescope. This is called collimator. This collimator has got a small opening here, or opening means a small slit. Okay. So when you place a light source over here, that is when you place a light source here, light from the source will enter through the opening or slit of the collimator. It will fall on the prism that is placed here. So when it enters, it will get reflected and it will enter, the reflected ray will enter through this telescope. This telescope has got cross wires, both horizontal and vertical. By seeing where it coincides, you can take the reading. So you can see the image of the slit through the telescope. Okay. Now this one is actually a table which has got, see here you can see two readings there. It has got both main scale and vernier scale. This also will have main scale and vernier scale. That is from where you take the readings. Okay, let us see how experiment is performed. Before starting the experiment, there are a lot of preliminary adjustments. Let us see which are they. To find angle of prism, first least count of the vernier is noted. The preliminary adjustment of the spectrometer consists of adjustments to the telescope, prism table and collimator. You have to do preliminary adjustments to each of these. The telescope has preliminary adjustment as well as collimator and prism table. First, you adjust the eyepiece of the telescope so that cross wires are correctly found. The next step is that you just rotate or swing the telescope to one side and focus on any distant object until you get a clear image of the distant object through the telescope. If you are not getting the clear image, you have to focus the telescope until you get a clear image using the rack and pinion arrangement. This is the rack and pinion arrangement. You adjust the screw until you get a clear image of the distant object. Okay, and the image thus obtained should not have any parallax also. Once these adjustments are made, then the instrument should not be disturbed. After that, as I already said, you have to place a light source in front of the slit or opening of the collimator. Now that you can view the image of the slit through the telescope. Now adjust the collimator lens using that similar rack and pinion arrangement that is provided there until you get a sharp image of the slit. Now we say that telescope is ready to receive parallel rays. The prism table is leveled and we have to mount or place the prism on the prism table. Now everything is set for measurement. So see, this is a schematic diagram. This is a prism table. You have placed the prism there. It is marked as A, B, C. Here you have the telescope, and this is not another telescope. This is actually the position after the telescope is being rotated. Then the above one, this one is the collimator. Okay, this is a collimator. Now the vernier table is rotated so that edge of the prism points towards collimator. See the edge of the prism, which is the edge, it is marked as A of the prism. That is the edge of the prism. It is facing the collimator. Now the parallel rays of light from the collimator fall equally on the faces AB and AC of the prism. Vernier table is clamped. Now you should not disturb the vernier table. Now what is next? The reflected image of the slit from face AB is obtained through the telescope. See, from the collimator, the light ray falls here and it is reflected, and the reflected ray from the face AB of the prism will be received at the telescope. Now you just note the main scale reading and vernier scale reading, and after that you just rotate this telescope to the other side of the prism. From the other side of the prism also, you will see the reflected image of the slit from the face AC of the prism. From there also you note the main scale reading and vernier scale reading. Now the difference between those readings will give you twice the value of angle of prism. So from that you will get the value of A. Usually you will get the value of 2A as 120 degree. So angle of prism A will be 60 degree. That is how the angle of prism is measured. That is what it is described in this small paragraph. So when you do this experiment, everything will be clear. Now you just read the paragraph. So that's all about the instruments used for measuring angle. Next we will see the measurement of current and voltage using galvanometer. Okay. Galvanometer consists of a rectangular coil of insulated copper wire which is wound over a light metal frame with many turns, which is free to rotate about a fixed axis in the presence of a magnetic field. It has a cylindrical soft end core, and it is mainly used to make the field radial, or it is mainly used to increase the strength of the magnetic field. So let us see what happens when current flows. When current flows through the coil, a torque acts on it. So the torque produced by this current flow is called magnetic torque. Okay. Now this magnetic torque will rotate the coil. Now there is a spring there, and it will provide a counter torque. That is, it will oppose the magnetic torque. That is, it just balances the magnetic torque. Now thereby producing a steady deflection. This deflection will be indicated on a scale by a pointer which is attached to a spring. So let I be the current through the coil of area A having number of turns capital letter N. Then the torque will be given by tau equal to N I A B. Due to this tau, the coil rotates. When the coil rotates, the spring attached to it will wind up, thereby producing a restoring tau on the coil. This restoring tau will be proportional to the angle of deflection of pointer attached to the string. Okay, now this nothing to explain, everything is written in simple sentences. You just read through it. First, it actually tells us about the construction of the galvanometer, and after they are telling about what happens when current flows through what all things happen when current flows through the coil, and then finally an expression. Okay, if K is the restoring tau per unit deflection and alpha is the deflection produced by coil, then tau will be equal to K alpha. When restoring tau becomes equal to deflection tau, then equilibrium will be established. So at equilibrium, we can write a condition, that is NIAB. What was NIAB? The magnetic torque or torque produced by the current flow through the coil will be equal to K alpha. From that, you can find the value of current I. So the deflection alpha is proportional to current through galvanometer. It is given by alpha by I equal to NAB by K. That term is called current sensitivity of the galvanometer, or it is defined as the deflection produced per unit current. Galvanometer is a sensitive equipment. Very low voltages and current can be measured using that. But for measuring large current and voltage, it cannot be used so much. Now a galvanometer can be converted into ammeter to measure current, or it can also be converted to voltmeter to measure voltage. Okay. Now let us see the conversion of galvanometer into ammeter first. As I already said, ammeter is an instrument used to measure current in an electrical circuit. It is always connected in series with the circuit. The ammeter must have a low resistance instrument Okay, so it is just enough to study this sentence. That is, ammeter is a device used to measure current in an electric circuit. Now you can convert a galvanometer into an ammeter by connecting a small resistance or a low resistance called shunt resistance in parallel with it, as shown in the figure. See, this is a galvanometer. You are connecting a low resistance called shunt resistance parallel to galvanometer G. Okay. Let Ig be the maximum current that can be passed through the galvanometer. Let G be the resistance of the galvanometer. Now to convert this galvanometer into ammeter, you have connected a low resistance called shunt resistance S parallel to it. Now current through the shunt resistance will be I minus Ig as shown in figure. It is marked there, I minus Ig. Now since galvanometer and shunt are parallel, the potential difference or voltage across galvanometer will be equal to the potential difference or voltage across shunt resistance. So you can equate that. That is IgG. That is actually I into V. What is IV into I? I into R. That is actually potential difference voltage, right? So current through galvanometer Ig into resistance of galvanometer G. That will be the potential difference across the galvanometer. Now potential difference across the shunt resistance will be the product of current through the shunt resistance and the value of resistance of the shunt resistance. Okay. So that you can equate, and from that you can find the value of S or the value of shunt resistance S. So this value S will be the value of shunt that you have to connect in parallel to the galvanometer in order to convert into an ammeter. Okay, now the effective resistance of ammeter, there is another expression. It is given by Ra equal to Gs by G plus S. G is the resistance of galvanometer, and what is S? The shunt resistance that we are connected in parallel with galvanometer. Now the resistance of ammeter is very smaller than G, so when connected in the circuit, it will not affect the current passing through the circuit. Now the similar expression with a slight changes will be there if you are converting the galvanometer into a voltmeter. Voltmeter is nothing but a device used to measure the voltage or potential difference across any 2 points in an electrical circuit. In order to convert a galvanometer into a voltmeter, what you have to do is that you have to connect a high resistance R in series with the galvanometer G. So it's just not the difference. If you want to convert a galvanometer into an ammeter, what you do, you connect a low resistance, that is shunt resistance, parallel to it. If you want to convert a galvanometer into a voltmeter, you have to connect a high resistance R in series with it. Okay. Now as explained before, let Ig be the maximum current that can be passed through the galvanometer of resistance G, and to convert this into a voltmeter, a high resistance R is connected in series with it. So the potential across G, that is V, and it will be equal to the potential across the high resistance I, that will be Ig R plus G. So from that you can find the value of the high resistance R that was connected in series with the galvanometer. It's nothing, R equal to V by Ig minus G. So this is a value of resistance to be connected in series to convert the galvanometer into voltmeter. Now the effective resistance of voltmeter is G plus R, which is very high, so it will not draw much current from the circuit. So today we have learned about instruments used for measuring angle, and I have learned about the measurement of current in electrical circuit using galvanometer, how a galvanometer can be converted into ammeter and voltmeter. So with this class we have finished the first half of our module 3, that is experimental methods and error analysis. So the first half actually dealt with, as I already said, it was measuring instruments. Now in the next class we will learn about the second half of the same module, and that second half actually deals with error analysis. Okay, so along with this today's video, I will also upload a few sample problems which is already solved, and also some sample questions that you can go through with some sample problems which you can work out. Okay, mainly from this particular topic, I mean from measuring instruments. Okay. Okay, that's all for today. Thank you.